Application for testing and optimizing the performance of electric power systems in a hybrid MELEX vehicle. To begin with, I would like to present briefly the plan of presentation. Introduction, power supply systems in an electrical vehicle, the measuring station, results, conclusions. The popularity of electric cars now is growing, although cars with internal combustion engines still dominate the roads. Car companies are trying to encourage customers to buy electric or hybrid cars. Such solutions save fuel consumption while reducing emissions. When comparing the performance of electric motors to internal combustion engines, we can see a significant difference. Electric units have an efficiency of more than 90%, which means that a large part of the energy is converted into mechanical work. That directly drives the vehicle. The efficiency of the classic internal combustion engine is around 33%. Mechanical losses from multiple mechanisms such as the clutch or gearbox have to be accounted for. We can then estimate the efficiency at the drive wheels at around 16%. The advantages of using electric drives are numerous. Compared to internal combustion drives, electric motors are cheap to operate. Electric motors are much simpler in their design and can be easily controlled. They have high torque at both low and maximum revs, which makes a gearbox redundant in such vehicles. Very importantly, the vehicles do not emit pollutants into the atmosphere and there is not a lot of noise during their operation, making them environmentally friendly. The use of electric and hybrid drives in cars requires the user to control the discharge of the batteries responsible for supplying energy to the car's electric motor. Estimating the range that a car can cover on its current battery charge is essential for planning a route or recharging the batteries before embarking on a long journey. It is also necessary to implement systems that inform the vehicle user of the status of parameters relating to the operation of the entire car. The object of this presentation is investigating a specific design solution for a MELEX type vehicle. In its original version, this popular brand of electric vehicle has been and continues to be used in a wide range of locations, including industrial sites, camping areas, golf courses and other places where a quiet, environmentally friendly and fuel-efficient form of transport is needed. MELEX vehicles are characterized by their simple and robust design and ease of operation. Depending on the model, they can carry between 2 and 8 passengers and have a range of 50 to even 100 kilometers. The MELEXs are fully electric and are equipped with batteries that can be charged from a socket. Among the MELEX models, you can find vehicles of different sizes and specifications, including models for goods transport and specialized vehicles with ramps for disabled people. The main objective of the study was to investigate the performance of the power systems in a modified MELEX electric vehicle. To achieve the goal, the electric vehicle was upgraded with an additional internal combustion engine together with alternators to provide a source of electrical charge for the lead-acid battery pack already in use, being the primary power source for the vehicle's electric motor. Subsequently, a measurement system for monitoring the vehicle's electrical parameters was designed and implemented, and an application with a graphical interface to display current information about the vehicle's power system was developed. The final stage of the work was to verify the correct operation of the measurement system, checking the operation of the vehicle's power supply system, charging the battery pack using alternators driven by an internal combustion engine. The test subject was a retrofitted MELEX electric vehicle. The original 1.6 kW electric motor was left in the vehicle, but its location was changed by rotating the rear axle 180 degrees. 3 12V lead-acid batteries with a capacity of 62 Ah each were used as the power source. A DC motor controller, built on an Arduino Uno microcontroller and IGBT transistors, was used as the speed controller. The vehicle was also fitted with an internal combustion engine from a Fiat 126P vehicle, retrofitted with 3 alternators to recharge the batteries while driving. The dashboard was provided with switches to switch on the electric motor, a switch to change the travel direction, and 3 switches to switch on battery charging via the alternators. In order to read the voltages on the individual batteries in the application displayed on the touchscreen, it was necessary to process the signal so that it was readable by the microcomputer. To begin with, the voltage signal from the battery was passed through a voltage divider to bring it to a readable value for the Arduino Uno and Mega platforms. The Arduino inputs allow to measure voltage between 0V and 5V. This way voltage can be measured with the accuracy of 5 mV. After passing the signal through the RC filter, the noise was reduced and the signal was readable by the analog input of the Atmega 168 microcontroller. Then using the Arduino Uno platform, the analog voltage signal is converted into a digital PMW signal and passed to the opto-isolator for further transmission to the Arduino Mega, which shares the ground terminal with the Raspberry Pi microcomputer. The opto-isolator system is only used for battery 2 and 3, because they are not on a common main ground bus. At the output of the opto-isolator, we also get a PWM signal, but already on the main ground bus, which is converted by the RC low-pass filter into an analog signal that is readable by the Arduino Mega collecting all the signals. During initial testing, it was noticed that the voltage signal coming out of the battery is very much affected by the running electric motor, making it unreadable to the Arduino, and has to undergo a filtering process. Therefore, a low-pass first-order RC active filter with the frequency of 3.39 Hz was used. After passing the signal through the RC filter, the noise was reduced and the signal was readable by the analog input of the Atmega 168 microcontroller. Figure A shows the voltage signal after the voltage divider before the RC filter, and Figure B shows the signal after the RC filter. In order to read the value of the alternator charging current for the individual batteries, as well as the value of the total current feeding the electric motor, it is also necessary to convert the signal into a voltage analog form so that it is readable by the Arduino platform. On the basis of preliminary tests, it was found that current measurement using 100 mV/75A shunts was not possible due to the interference generated by the operation of the electric motor and its controller during operation. The electric motor introduces high noise into the measurement system, making the shunt reading unreadable, and the noise level generated, despite the use of higher-order active filters, was significant, resulting in a large measurement error. In order to measure the currents in the system, the HLSR50 current sensor was used, which can be used to electronically measure DC, AC current, with galvanic separation between the primary and secondary drain. It features a multi-band open-loop current transducer, voltage, output, single 5V supply, low power consumption, high bandwidth, and has a magnetic core with very low loss. The measuring range of the HLSR50 sensor is plus 125A. The voltage signal from the HLSR50 current sensor is considerably less distorted than was the case with the measuring shunt, but there is still interference from the electric motor. The signal, therefore, has to undergo a filtering process, similar to the battery voltage signal. Here, too, a first-order RC active low-pass filter is used. The signal coming out of the HLSR50 current sensor is the input for the RC filter. Its parameters are identical to the earlier case, that is the filter cutoff frequency is 3.39 Hz. Signals from 4 separate HLSR50 current sensors, filtered through RC filters, go to the analog inputs of both the Arduino Uno and Arduino Mega chips. For Arduino Uno platforms, the analog signals are converted into PWM signals. These signals are then output to the opto-isolators. At the output of the opto-isolator, we get PWM signals, which are converted by low-pass RC filters back into analog signals for the Arduino Mega platform collecting all the signals from the HLSR50 current sensors. The Raspberry Pi microcomputer on which the vehicle performance monitoring application is installed is connected to a capacitive touchscreen designed for the Raspberry Pi. The screen is connected to the microcomputer via a dedicated DSI connector and is used to display an application written on the microcomputer to display the parameters of the batteries that power the electric engine and alternators while the vehicle is running. A Python application has been written for the Raspberry Pi microcomputer to measure the parameters of the vehicle's power system during operation. The application collects data on the voltage and current of the vehicle from the Arduino Mega. The screen displays the information on the voltages of the individual batteries and the alternator charging current. The acquired data are saved in separate files to allow data collection for research purposes. Data logging can be enabled via the main screen, which means that the collected data will be saved in a text file on the Raspberry Pi microcomputer. The user can select parameter monitoring or data logging button on the main screen. Selecting one of the parameter monitoring buttons will take the user from the main panel to a panel where the real-time values of the system parameters can be observed. On panel can be displaying information on the values related to the voltage and current drawn from the batteries by the electric motor. By pressing the back button, the user returns to the main screen. Pressing the graph buttons during data logging will display a graph of the data collected by the application. The graphs update continuously as more data are collected. The test object is the power supply system for only the electric motor of a MELEX type vehicle. The aim of the tests is to check the total power consumed, the instantaneous power, the individual voltages on the batteries and the load current during the operation of the electric motor alone. Using the developed application, data collected in tabular form were then processed in the MATLAB environment. The test lasted 90s with a variable load on the electric motor. In order to simulate the driving conditions of the vehicle, the engine speed was modulated by varying the degree to which the accelerator pedal was depressed, while at the same time the brake was applied, causing the load on the electric motor to increase and decrease. The purpose of the test was to check the operation of the electric motor under variable load in the form of modulation of the degree of depressing the accelerator pedal and the brake. The entire test lasted 90s. The electric motor was switched on in the 5th second of the test. The speed at which the wheels of the vehicle rotated was variable. The value of the load current during electric motor operation was at varying levels, as can be seen in Figure G in the 75th second of the test. The motor draws 60 A, which is the peak value. During the operation of the electric motor, varying voltage drops on the batteries were noted, related to the uneven load current during operation, as shown in Figures D, E, and F. The total voltage on the battery pack supplying power to the engine, while it was running, also varied and depended on the load on the batteries, as can be seen in Figure C. The peak instantaneous power reached 2.2 kilowatts in the 75th second of the test. As shown in Figure B, the total power consumed by the system during its operation was 0.0265 kilowatts-hour. As shown in Figure A, the electric motor was switched off after 78 seconds of the test. As can be seen from the accompanying diagrams, despite significant noise caused by the electric motor running, the signals transmitted to the Arduino Mega are still clear and reflect the actual behavior of the system. The test subject is the electric and internal combustion engine power supply system of a MELEX vehicle. The object of the study is to monitor the battery voltages and currents with which the alternators recharge the battery pack while the internal combustion engine is running and the electric drive is switched on. The test lasted 125 seconds with the internal combustion engine running at a constant speed of 3000 revolutions per minute and with a variable load on the electric motor. In order to simulate the driving conditions of the vehicle, the electric engine speed was modulated by varying the degree to which the accelerator pedal was depressed, causing the load on the electric motor to increase and decrease. The test carried out was to check the operation of the internal combustion engine together with the alternators that charge batteries 1 and 2. The electric motor was on during the test. The entire test lasted 125 s. Alternators 1 and 2 were switched on during the test from T equals 5s to T equals 95s, while the internal combustion engine was running. The third alternator has failed, resulting in a failure to charge battery 3, as can be seen in Figure I, where the voltage value on the battery is kept constant. During the operation of alternators 1 and 2, the voltage on batteries 1 and 2 rises above 14 V, indicating correct operation of the charging system. As can be seen in Figures G and H, the voltage value across the battery pack jumped to 42 V when the alternators were switched on. As shown in Figure F, the value of the charging current can be observed in Figures C and D. Peak instantaneous power reached 0.65 kilowatts in the 72nd second of the test, which is presented in Figure B. The total power consumed by the system during its operation was 0.0065 kilowatts-hour, which is presented in Figure A. During the test, the vehicle was traveling at varying speeds, from T equals 35s to T equals 55s. The electric motor was switched off while the alternators charged the batteries all the time. The propulsion system in the built MELEX vehicle is an electric motor, with the internal combustion engine serving as a generator to charge the battery pack while driving. The hybrid system complements each other. The internal combustion engine with alternators provides additional electrical energy and transfers it to the batteries. Thus, the running time of the electric motor is increased, extending the distance that can be covered with the batteries. The internal combustion engine can run while the MELEX vehicle is in motion as well as when stationary independently of the electric motor. To ensure the best interaction between these devices, a system is required to monitor the electrical and mechanical power supply parameters. Monitoring of the power systems allows controlling the consumption of the battery pack. When the electric motor loses power, the combustion engine will allow energy to be supplied to the battery pack without discharging the energy carrier. While the vehicle is in operation, all measured parameters are stored in the microcomputer's memory, allowing the performance of the power systems to be analyzed and optimized. Here's the list of reference. Thank you for your attention.